Perfect.
Okay. So for the last session today, we have Edgar Pimentel from Universidade de Coimbra. Edgar.
Thank you. Thank you, Ricardo, for the introduction. And I want to start by thanking the organizers and especially Ricardo for the invitation. When I got this invitation for the celebration of Carlos Tomei, first I thought it was a prank, right? So I started looking in the email for this link that says, well, you're invited, you have to wire 10,000 euros, and then I didn't find the link, and I started thinking this could be a serious invitation. And I was very happy and very honored. And well, the reason why I was very happy is that in 2016, I applied for a job here in this university. And for some reason that I also thought it was a prank, they invited me for an interview, right? And I arrived here, and the person in charge of the interview was Carlos Tomei, right? So I went to his office, and he had biked his way here, and he said, well, I just have to change clothes, and we'll start the interview. To which I thought, well, maybe he's going somewhere else to change clothes, right? My mistake. The guy starts changing in front of me, and well, that's all about that for traumatic, right? And I said, well, I want to work here. This is the place for me to work, right? And I started here in the January after that, in 2017. And it was one of the best decisions I made in my professional and my personal life. I started having lunch with Carlos Tomei and Nicolau Saldanha on a daily basis, right? And I assure you, this is a postdoc. You see? Yeah, because you go for lunch, and then you start learning about this thing, toda flow, right? You start learning about 3n plus 1. You start learning about things that fold somehow, right? And then you have a line, and everything is infinite dimensional, and it's very beautiful. But then you also start learning about these things. Well, if you want to teach mathematics to the new undergrad students, then maybe you should think about those things. Maybe you should think about those other things. Maybe why not to have computers in the first year's courses, right? The calculus, linear algebra, and things like those. So the thing is, my impression and what I'm trying to convey here is that by interacting with you, I learned a lot of mathematics. I learned a lot about how to do mathematics and how to think the university, right? Because you're a guy that thinks about the L infinity norm, but you also think about the L1 norm, right? And if you interpolate this whole thing, you are everywhere, right? So I think this institution owes you a lot in the way it works, in the way it thinks. And I think everyone that has the privilege of having you as a colleague also owe you a lot. And I want to thank you for that. Right? And this is the important part of my talk. I mean, if you want to go home, this is the moment. I mean, I'm talking math now. And, well, the reason I chose this topic, numerical methods, I never did numerics, and this is my first adventure in the numerical thing, is because once upon a time, right, there was Carlos Tomei, and he said, well, there is this matrix. In the diagonal, you have 2, 2, 2, 2, 2. And in the secondary diagonals, you have minus 1. I mean, secondary diagonals, I don't know if it exists. But you know, it's this thing very close to diagonal, right? 1, 1, 1, or minus. There is a minus somewhere. And I was staring at that, and he said, this is the Laplace operator. And I said, really? Is this the Laplace operator? And indeed it is. And the thing for me was that still there are things that I don't understand from our talks, right? I started understanding a few things, and that's what I'm talking about today, Okay. So, well, we're talking about numerical methods for fully nonlinear free boundary problems. So let me start by telling you something that has to do with the pure equation. So we have a fully nonlinear operator, and we have an equation like this. Okay. And let's say it holds in a domain omega. The domain omega is a subset in RD. It has a uniform exterior cone conditions and things like those, and all the theory here works. You can equip this guy with boundary conditions, right? And then you can.
What do we know about capital F?
Capital F is you can think of this as a function from symmetric matrices to the line, and you can think this is uniformly elliptic. So if you want to feel comfortable about F, you can imagine that F is the trace of Ax d2u, where A is such that Ax psi transposed is bounded from below by some lambda psi square, and from above by capital lambda psi square, something like this, right? Things can get frisky if you have here some index, and then you take infimum on this index, and then it's now nonlinear, and it's an example of something like this, right? So it's a lambda uniform elliptic operator. You can think of the Laplace operator, right? The Laplacian, right? Whenever I write F, you can think of the trace.
Laplacian would be trace.
It would be trace. You can complicate trace the way you want. I mean, people want to write papers, right? So then you change Laplace. But that's what it is. And well, this is I don't dare adding any sort of reference for this, but for this type of equation, if someone is interested in that, then there is this classical book by Luis Caffarelli and Xavier Cabré. This is 95, and has to do with the viscosity, the theory of viscosity solutions to this class of problems, right? But then you see, this is something that is uniformly elliptic. And what happens is that you may say, well, instead of being uniformly elliptic, we may ask or we may allow this equation to degenerate somehow. And the way we choose this to be degenerate is by multiplying the operator by the norm of the gradient raised to our favorite power. Let's call this theta, f d2u equals f in the same domain or something like this, and then you equip this guy with boundary conditions, right? And this model was introduced around 2007 in the works of Szabó Birindell and Françoise de Mengel, and was studied by a number of authors, including Cyril Imbert, Luis Silvestre, and Eduardo Teixeira, and a number of other authors. And there is a recent contribution to the boundary regularity to this problem. There is due to Damião Araújo and Boyan Sirakov. And I mean, this is an interesting model, and it continues to attract the interest of a lot of people. What we want to do is to embed these models in the context of a free boundary problem, right?
The exponent theta is a constant.
It's a constant here.
What do we know about the constant?
We know that it's a Greek letter. We know it's, let's say, it's above 1. And it's a constant that is strictly greater than 1. Something like this, right? And what we want to do is to embed these things in free boundary problems. So the free boundary problem, I'll call this FBP1, will be like this. Will be F1 d2u, let's say, equals to 1 in omega, enter the region where the solution is positive, right? And then I have F2 d2u is 1 in omega where the region is negative. And then you can prescribe some Dirichlet boundary conditions to this problem as well. So you see what's happening here is, well, When solution is positive, diffusion is driven by F1. In the trace of A of X, in the positive phase, you have a matrix A, right? In the negative phase, you have a matrix B, let's say, right? But you have different diffusion processes taking place in different subregions of the domain, right? And when it comes to this degenerate problem, then what you have is a free boundary problem 2. There would be, let's say, du to a power theta 1 f d2u equals 1. In the positive phase, I'll denote this guy with omega plus. And, well, du theta 2 f d2u equals 1 in omega minus, right? And so what happens here, and what is interesting here, is that, well, you see, here, if I have this degeneracy rate, or this 1, it depends on the sign of the solution. But you see, for me to figure out the sign of the solution, I have to know where each one of the operators are binding, right? Or are in place. So this is the difficulty here. And what's more important is that properties like monotonicity for this operator with respect to the solution are far from clear, right? It's not something that you derive immediately. So these are the problems that we want to attack from the numerical viewpoint. And, well, what we know about these guys, so let me tell you a few things. So the first problem, FBP1, so this guy was studied, to the best of my knowledge, for the first time by Maxon Santos and a collaborator. And actually, it was in his PhD thesis that was completed here, and the committee had Professor Nuzenschweig Lopes, Professor Nicolau, and some other friends of ours. But well, that problem appeared here in Maxon thesis, and it was somewhere in some paper out in 2023. And what is done there is analysis of the regularity of solutions. So what is proven is that in some points along the free boundary, solutions are of class C11, right, which is optimal for some reason. The existence and uniqueness of solutions to that problem was studied by Andrei Schfiel in 2022 and a collaborator. And what they proved is that, well, if these operators are uniformly elliptic, then there exists a solution to this problem. There is no uniqueness, but there is the solution. I'm not saying that there is no uniqueness. The result is not on the uniqueness, right? But if you have F1 and F2, then you have a solution, a viscosity solution to that problem, C1 alpha for some alpha that is universal. And if these guys are convex or near convex operators, then it happens that solutions are W2P for P above some certain magical number, and therefore you have strong solutions for the problem as well. And this is in this paper. And about the free boundary problem 2, then there is a contribution by Gerardo Warotto, Gianni Rampasso, Andrei Schfiel, and this so-called collaborator of them, where for this problem here, they study the existence of viscosity solutions and prove the optimal regularity in some C1 alpha space. Yes?
Yes, you got to help me here. So you have two sort of subdomains, and the free boundary is the interface.
Yeah.
What is the free boundary?
The free boundary is the interface. So the thing is, this is omega, right? And you have something like this. Let's say this is U positive, U negative. This is U0, you don't care. But this thing here is the free boundary.
In extreme what sense, since there's no time, is it a boundary to be determined? Is it free?
It's endogenously determined, you see? Yeah, I mean, this is the term together with the solution itself.
Okay.
Right? So the question is, the thing here is, well, from the viewpoint of regularity theory, if you're inside any one of those subdomains, then you have interior regularity, right? This is known to the Greeks from the 80s, right? The Greeks from 1980. But the question is, what happens if you are on a point at the free boundary, right? Because then you move across, and then hell breaks loose. And then, I mean, and then you need something.
Do you know anything about the boundary itself? Regularity?
This thing here, yes. In this case here, at some point, you can say the free boundary is C1, or C1 alpha, or something like this. Yeah, the optimal regularity one would expect C11, I guess. But that's, well.
So they have to join with a certain regularity there, this sort of branching you did?
Not really. Not really. We wish so, right? Okay. We wish so. There are a few things that we did recently that has to do with the regularity at the intersection of the free boundary and the fixed boundary, right? There is also some sort of mystery happening at this level as well. But it's something that, well, with luck, sometimes it will be out. Sorry?
Cusp.
Yeah, maybe, but that's just this drawing. There could be a theorem that says there are no cusps. There can never be cusps. Or this type of question could be important. I mean, these two portions of the free boundary, should they intersect transversally or non-transversally? Or this type of question makes sense. But it's something we don't know.
Do you have uniqueness? I didn't get it.
No.
Never.
No.
Never have uniqueness.
No, and that's why numerical methods would be interesting.
Well, I mean, if you don't
Because they give you.
have uniqueness numerically. Well,
No, if you don't have uniqueness to this problem, right? But you'll never operate numerically at the level of this problem. You'll have to do.
go ahead.
Yeah, you'll have to see the talk, right? But that's it. And well, what happened here was, well, for this second problem, we studied the optimal regularity and the existence of solutions. And this is 24. This is Annals PDEs. And this is just something that is a year old or so. So you see what happens. Let's focus on this guy here, because then we have a few interesting things to share with you from the numerical viewpoint. And what happens here is, well, you see where the solution is negative, right? So I have this theta 2 guy, and then when the solution is positive, then I have the theta 1, right? So what I'm saying is, well, I'm jumping from one to the other, right? And this is not a nice thing, because I'm jumping from these guys, I don't know what's happening. It's not something that you can somehow say, well, let's do numerics at the level of FBP2, right? I don't know how to do it. But then what you can do here is to say, well, you fix an epsilon, right? It's like one of those calculus things. You fix an epsilon, right? So you fix this guy, and you think in terms of minus epsilon plus epsilon. And whenever the solution is below minus epsilon, then you ask, well, you are theta 2, right? Why not? But then, if you are above, you are theta 1. It's cute, right? The thing is, here, you go linear, right? You go linear. And then you have a Lipschitz function. Cute, but only Lipschitz. But then you convolve, right? You go to the appendix in Evan's book, you learn everything there is to know about mollifying kernels, and you convolve this guy. And then you end up with an exponent, there is theta epsilon, that depends on t, let's say. And then, well, you start with this epsilon guy, right? It's your favorite small number, it helps you save in the day. So what you do is, well, you change a bit this guy. What you do is, you replace FBP2 with epsilon, U epsilon. It's very good for your health, for comparison principle, right? Plus the gradient of this guy, everything raised to this exponent.
Sorry, what is U epsilon?
Is the solution to an equation I'm about to write. It's a function no. I'm writing a PDE.
So it's epsilon is just an index.
It's just an index, yes.
For each epsilon, there is a solution.
I'm christening the function, right? I'm just giving a name, right? And then what I do, no, I don't do this like this, I do like this. Right? And this is, let's say, equal to 1. You see, this is an approximate problem. This is an epsilon approximation of my problem, right? In which sense? This is no longer degenerate because epsilon prevents this whole thing from being 0, right? I have here a positive epsilon times the function, so this is screaming maximum principle, which is a very good thing, right? And here I have my operator. So this guy here defines, let's say, an F epsilon of M, P, R, and X if I want, right? There is my new operator.
I'm still very worried about the capital F, which, do we still know nothing about the capital F?
Capital F is the Laplacian.
Oh.
Yeah, but I don't want to write the Laplacian. I want to write capital F. It's a new trend in Coimbra now. We are starting this. This is a fully nonlinear lambda-lambda elliptic operator. For instance, the Laplace operator.
Okay.
Right? Yeah. And, well, now we have this guy. And this guy is good, right? This guy is uniformly elliptic in terms of this quantity. And for every fixed epsilon, I can come up with a solution to this guy, right? And the solution to this guy, as epsilon goes to 0, approaches or converges to a solution of this equation here, right? So what we want to do is to propose a numerical method for this guy here. Right? So what we need to do is to come up with a numerical method to approximate viscosity solutions to a fully nonlinear equation, right? And well, when we think in terms of this question, then it was done. Yeah.
What is the regularity expected for the solution of this equation? Because now
The approximate one
this is the regularity. Yes. Of
for this, I don't know and I don't care. Yeah, should be some C1 alpha.
with alpha depends on this equation.
Depending on the moon, right? So what we want to do is now to discretize the domain of this guy and propose a discretization. Of course, we have to think in terms of this, of the norm of the gradient, and we'll evoke some upwind strategy. And for the Haitian, we have to make some assumptions on the fully nonlinear operator, right? But what we want to do is to discretize this problem equipped with a Dirichlet boundary condition and then study the convergence of this problem, right? So what we need to do. So you see, in 1991, Gibarle and Takis Souganidis studied a numerical approximation. Actually, not a numerical approximation at first, it's a very abstract framework, but an approximation for the solutions, for the viscosity solutions to fully nonlinear equations. Hamilton-Jacobi equations, first order problems, and second order fully nonlinear equations, right? And a couple of years later, Adam Obermann, and this will be 2006, and this is Siam Journal Numerical Analysis. What Adam Obermann studied was some sort of kind of an implementation, but it's still very, very theoretical, of the ideas introduced here. So basically, what we need to do to evoke this machinery of shelf somehow, right, would be to prove a few things. So now, yep.
Before you go on, just a question. Go on the left-hand side of this equation, blah, 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 say capital G, okay? G epsilon G
Yes.
is what, okay?
Yeah, I'm doing that.
Is there a plausible linearization for that? Can you talk about local invertibility?
I don't know. Probably yes. Probably yes. But I don't know about those guys.
So you can prove that the solution exists here. For any answer.
Here? Yes. But the way I do it here is I prove a maximum principle, comparison principle actually, come up with barriers, global barriers, and evoke Perron's method. And that's how solutions to this problem will exist. And that's the strategy. Yeah. So you see what happens here is that, well, we fix then a very small number h, right? And we approximate this guy, we approximate the closure of the domain with a regular grid at this point. I'm not focused on the efficiency, accuracy, or how fast the method is, or how many cores I need to make a colorful picture of whatever. I'm focused on solving this thing numerically, no matter how, right? So I have the domain, I discretize the domain, how do I say? I put everything together with the boundary, also discretized, and then I come up with something. There is a G, epsilon h of this guy that I define as this quantity here that I will call just merely G epsilon minus 1 if x is in the interior, is an interior point of my grid, and UH minus the boundary condition of my original initial problem, right, is if x is on this boundary, right? There is one thing here that I'm kind of cheating, because one interesting thing is to say, well, instead of saying x on the boundary, I could say, well, I kind of extend a bit the domain, I discretize the whole thing, and I impose the boundary condition outside of the domain in this extended thing. This is what I mean by that, right? And, well, this will be my...
Do you want to do that, or could you have picked omega h equals to omega? You want to be larger, or is something...
I mean, depends on the geometry of omega, right?
If you have a polygonal...
If I have a square, I don't need to do that. Yeah, if I have a square, I don't need to do that. But if I have the drawing that I have here, maybe it's useful. And now what happens is, well,
Just a spoiler. Which numerical method do you have in mind here?
an artificial Euler. An artificial Euler thing. Yeah. I'll pretend this is time dependent.
Yeah, but this is not a numerical method. So if you have a time dependent, you want to reach.
Oh, I see. This is how I solve it, right?
Yeah.
The numerical method is this. So I will discretize the gradient using an upwind thing that has to do with the square.
Finite difference.
Finite differences, yes. This is a way to put it. Yeah. So what's happening here is, well, now this guy here.
I'm sorry. What happened to the theta when you discretized? The exponent theta, which was supposed to theta 1, theta 2.
Will be evaluated on this function here on grid points, right?
So you don't really know if it's 0 or 1.
No. I discretize.
It's part of the unknown.
Yes.
Okay.
Yes. Is the function, right?
Okay.
Is the function. And now I want to solve this thing. Right? The correct way of doing this is by adding here I square and dividing this thing by 2, right? And the reason why I want to do that is because I want to write this thing as the sum with I from 1 to, let's say, D, the maximum of U H in the direction I, right? X minus square, right? So this is the square of the gradient. So this will be a choice for this guy in finite difference that will yield something that is monotone, right? In one direction. And then what happens is, what I suppose about F is that F is an Isaacs type of operator whose matrix satisfies some diagonal dominance condition. And then
So you're doing a difference between UIX minus UIX plus H.
Yeah.
And then you do UIX minus UI.
X plus age. And everything is age squared.
So in the brackets with the maximum, you have the same terms.
One is x plus h and the other one is x minus h.
Okay, but then you should have a forward finite difference and a backward finite differences.
Yes.
Together, really.
Yeah.
No, but so there is a wrong sign, I guess. But anyway.
But those things will be squared, right?
Okay.
So why do you need the next?
Because I want this to be monotone and consistent. And I want this thing to converge to what the gradient is, right? I don't know how much time do I have?
The maximum is because he's
I'm doing 20. I'm doing 20.
because he has absolute value.
I need to make sure that this is consistent with the gradient, the norm of the gradient square, right? And otherwise I don't have that. And that's something that will make the difference for me. And to discretize, well, and then I assume F to be an Isaacs type of operator driven by a matrix that somehow has this diagonal dominance condition. And then I use this centered finite differences for the Haitian, right? And I'm not writing this thing here. This is in archive as we used. And the interesting thing is that those things are consistent. This guy here, this approximation for the gradient square is consistent with the gradient square And if we have an Isaacs type of operator with diagonal dominance conditions, then this discretization of the Haitian actually converges is consistent with f d2u epsilon, right? And then, well, the theorem that we want to use, and there's a theorem that is here in this paper by Bartlett and Suganides, says, gives us the conditions we need to prove that this method here is consistent with this PDE equipped with a boundary condition governed by G, right? So the theorem in Bartlett, Suganides, 91, says that, well, let GH, age where it is, be a numerical method consistent with a given PDE if this is monotone and stable, then UH converges locally uniformly to U, where U solves the PDE and UH solves GH equals 0. So if I have a solution for the method, and I have a family of solutions for the method, then under the consistency with the PDE, monotonicity and stability, then this family of solutions converge to a solution of the PDE, right? And there is one thing here that is a bit tricky, because you see what happens. What happens is, well, let's say what we have is gradient square, right? And Nicolaus' favorite f, right? We have something like this. Right? So what we're doing, and let's say dimension is 1, right? So then we have our discretization of this guy, and we have this thing, let's say -1 equals 0, right? If this guy is monotone, and this guy is monotone, there's no reason whatsoever to conclude that the product is monotone, right? This is interesting, no? Right, you have monotone method, a monotone way of approximating this guy, right? It's a maximum of something. You have a discretization that is monotone for this part, but then you have the product, right? And this guy might have a sign that's, well, that you cannot bypass. So one thing is, well, but then you see, if this guy is 0, this is a bad thing, right? But if you have this guy here, an epsilon, why not, right? Then one thing that you can do is, well, if this is never 0, I can divide in the viscosity sense, right? And then I can divide in whatever sense I want, right? But I can divide in the viscosity sense, for instance. So what I have is that this guy here can be written like this. And this is monotone. It's cute, right? You see, something like this. And this is monotone, right? So you see, there is one problem with discretizing this equation, because regardless of the monotonicity for this piece and this part, I cannot assure that the product is monotone. So what we did, or what Ercilia did with this collaborator, was to say, well, if you write what we have here as epsilon u epsilon h plus f d2 h u epsilon h minus 1 over this is monotone. This is monotone in the sense of Bartlett-Souganides. In the sense of Bartlett-Souganides, which means what it means to be monotone is that if I have this and I have u h below vh, right? Then I have the operator at u greater than or equal the operator at v everywhere, right? So this is what it means. And this guy here is monotone. And then we can have a monotone method for this guy, right? So consistence follows from the definition and the choices of the discretization of the gradient and the Hessian. Monotonicity follows from a trick like this, right? And then the stability is quite funny because you see what happens to the stability is, well, you want to prove that, what you want to prove for the stability is that the supremum, where the supremum in H of the supremum in X of UH X is bounded by a constant, right? This constant may be dependent on several things, but it cannot depend on age, right? It has to be independent on age. And for us to prove something like this, what we do is, well, we come up with barriers, right? We come up with barriers, we have barriers at the continuum case, and we translate the barriers from the continuum case to the discrete one. But then there is a catch, and the catch is that, well, we don't know how this theta will affect, indeed, the comparison principle, right? But then what happens is, well, what we do is we choose a barrier that is large enough or negative enough so that we are never in the linear part of this theta, of the original theta. We are never in the transition part of the graph, so there we can compare, right? So we have consistency, we have monotonicity, and we have the stability that comes from the barrier. So then the theorem
So C doesn't blow up when epsilon goes to 0.
in which estimate?
Let's see. Could be 1 over epsilon?
Could be.
Could be.
Could be. But what happens is, all we need is for fixed epsilon, we need to prove this. Because what we do is something like this. What we do is, under the former yada yada, right? GH epsilon is consistent with this thing. There is the epsilon plus the u epsilon square theta u epsilon over 2 times this guy right? It's consistent with this guy, is monotone and stable. So I use the method to approximate this guy here. But when I approximate this guy, what I forget about the method, the numerical thing, right? I forget about that, and what I do is, well, I know from the Greeks, let's say, that this guy is uniformly bounded in some Hilbert space. uniformly in epsilon. And now I take limits, and I know this guy converges locally uniformly to a solution of the original problem, right? So the strategy is, well, I work at the level of this problem for the numerics, right? I do the numerics here, and then I invite the analysis to send this guy to 0. So we have 2 layers, right? The first layer is the age one. I don't care what happens at the level of epsilon. And the second layer is the layer of age, right? And well, the thing is more or less, once you approximate this guy numerically, then you get to this guy just sending epsilon to 0.
Do you have rates for age?
Nope. Nope. You know, we have these ideas that if something is semi-convex, this would be linear instead of the so-called half thing. There is one paper, very interesting paper by Maurizio Falcone. If I'm not mistaken, it's from 2016. It's in a book. But then there are some examples, some numerical examples, and there is one thing that is said there, that if you have a semi-concave solution or semi-convex, I don't remember, then you jump from the age to half to age, the rate. But I mean, this is something we didn't explore here, right? But this is a funny thing. This is a funny thing.
Those results are not with pi differences, I guess.
Yes, they are not. They are not. But there is
difference. I mean, your problem is not regular, right? I mean,
but there is this. But there are results by Jeff Calder, and with finite difference, where you can prove one side linear rate. Depending on semi-convexity or semi-concavity, you can prove one side linear rates, meaning that u age minus u is linear, or u minus u age, depending on whatever you're doing. And that's for finite differences in first order Hamilton-Jacobi equations. But here I don't know about rates. So I arrived here in Rio de Janeiro this morning, and I'm returning home tomorrow afternoon. So I'll ask you a couple of, only for Carlos, right? But I'll ask you 10 more minutes just to show you one thing that we did in the uniformly elliptic setting. Because you know, the uniformly elliptic setting has one thing that is quite funny. Because you know, you have this guy, F1, D2U is 1 somewhere, you don't know where. You have F2, you don't know where, right? And you want to do numerics here. And you don't know where you're doing numerics, so you go to MATLAB and you say, I don't know where this is like that. And then MATLAB says, come on, neither do I, right? So what do you do? What do you do? What you do is, well, you have an epsilon, right? Or an epsilon, it's a matter of taste. There's a positive number, and then you have a function v that is continuous up to the boundary of omega, right? And then what do you do? What you do is, I will exchange max and min, I never remember. But what you do is, you take the minimum between v plus epsilon over 2, epsilon and 1, and the maximum of these guys with 0, right? And you give this guy a name, right? This is age epsilon v of x, right? What I claim is that if v is smaller than minus epsilon, then this is 0. And if v is greater than epsilon, this is 1. Or this is some combination of max, min, 0, and 1. I mean, it's something that looks like that. It's in the paper, I don't remember. But that's what you do, right? And then you convolve age. Once again, you go to the appendix in Evans' book, right? And there is the modifier strategy. We do that. And once you do that, never know which side is the eraser, so. Once you do that, you have a new age, there is mollified, right? I'll keep notations. And then what you do is you have this thing, F1 plus F2m, right? And then you have a null operator. It's uniformly elliptic. It's very nice. It's regular in X. Of course, the regularity depends on epsilon, but who cares? You have now an operator, and here you can do numerics. What's the catch? The catch is that you have to send epsilon to 0, right? But you also have to find a fixed point with respect to V. This is something we did with Gerardo, Gianni, myself, and Andre in this paper from 2024. We proved the existence of a fixed point when we have functions, right? But then when we go numerical, to the numerical thing, it was a bit more difficult because I was thinking in terms of this guy as a discrete function, right? And then I had the impression that I was in the infinite dimensional world. Until the moment that I thought that, well, when I fix age, V is a guy here, right? So for fixed age, this is finite dimensional. Right? So this is analysis 0, right? Analysis -1. There is what I need. I mean, I can use a fixed point theorem at the discrete level as well. And then I have to prove that the thing at the fixed point is consistent and do whatever it does. And that's something we did with Ercilia recently. And that's what unlocked the numerical methods for the uniformly elliptic thing. This free boundary, the fully nonlinear free boundary problem in the uniformly elliptic setting. Right, so let me tell you a few things let me show you some numerical examples. And there is one thing about the numerical examples that I want to share with you that I find to be very funny. Sorry, guys. I left this institution with a very nice connection with everyone. I don't mean to destroy it. Yeah. Yeah. Deve ter. Deve ter.
In the meantime, let me make just a silly comment. When we teach baby calculus, we're constantly defining functions doing cases, right?
Yeah.
And it's more and more frequent that those cases get together with ReLU, for example, ReLU, right?
Yeah.
If, for example, you just add putting absolute values, right?
Yeah.
Which are the conditionals in the clauses, right?
Yeah.
And that's exactly what you do.
Yes. Yes. I know two or three things, right?
Absolute values by something smooths, right?
Yeah. 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 I know two or three things in life. I mean, either things are solvable using what I know or I'm doomed. So, yeah, I guess.
Can I ask a question meanwhile?
Sure.
Can you take, I'm scared with the theta of u, that's bad nonlinear. Can you take a log of this and bring the theta down?
In the estimates, that's what we do.
Oh.
In the estimates, that's what we do. I mean, when we prove a comparison principle, that's what we do. And then we use this inequalities book with many inequalities and hope something there saves the day. Well, so we have some numerical examples that we did with Ercilia. Ercilia is a colleague in Coimbra. So to put a face to the name, this one is Ercilia, this is myself, and this is one of our master students that were studying interesting things about that. The guy looks pretty happy here. Yeah, good. So this is our very small team in Coimbra. Well, so when it comes to the degenerate problem, well, this is the problem I show you, and this is the discrete monster we have, right? And the first example is logarithmic 1. So how we solve this thing is, well, this is our exact solution, right? And we compute what we have to do. We use an epsilon that is 0.01. And if I'm not mistaken, we are discretizing the interval a half to 1.5 and 100 points. And then we do some Euler, some artificial Euler, let's say, and there's a CFL condition that pops up and has to do with the data of the problem, but never mind. What happens is we start with this ansatz, this blue ansatz, right? And the behavior to the exact solution is like this. So it converges after a number of interactions in the Euler, this artificial Euler thing. And we notice that here the convergence is a bit slower. I mean, things detach from the linear ansatz, but here it's a bit slower, right? And we have still in the degenerate problem, and the error is something of the order 10 to the minus 4. And here is also 10 to the minus 4. And well, what happens here, the exact solution in this thing, for us it would be interesting to see what happens when we have kind of a plateau here. So we have 0 derivatives, and we want to really emphasize that, well, if we have 0 derivatives, the degenerate problem, that's where the devil is. And we also change the geometry from concave to convex, or the other way around. And the behavior is similar, right? I mean, we start with the linear ansatz, and it converges to where it has to go. When it comes to the uniform elliptic problem, then, well, we have this construction that I just show you to discretize the regularized version, the solution to the original problem. And then what we did was a planar example. And here we have trigonometric functions. What we have is the sine of pi x and sine of pi y. And well, because it does what we want, and it has this heat map for the error, the maximum thing goes also to the order 10 to the minus 4. So we have CFL conditions. If we violate, then of course this thing never works. But yes, that's what we do. One curiosity is that the first examples, the first and the second examples, we wrote the code, and Ercilia wrote most of the code because she's the one who knows this thing, some math lab, I guess. But this thing here was the code for this example was entirely generated by a large language model. And I'm kind of obsessed with this large language model. So we started in one, asked another one to improve, and came back, and those things. So there was minimal human intervention in the coding. And I mean, magically, it worked. So yes, so those were the results I prepared to share. Those are the examples I wanted to share. And Carlos, thank you, man. I mean, thank you for everything, and it's all yours. Thank you, guys. Yes.
Okay,
Please.
one way to prove that numerical methods converge to the PDE is to repeat the same argument. As if you said that you do Perron approach in the continuous sense, right?
Yes.
So try to do this numerically. So you go locally, solve,
Yes, yes.
start iterating.
We can do that, or we can go Bolzano. Yes, Bolzano. That's a funny thing, right? Because we have a barrier, there's a sub-solution, and a barrier, there's a super solution. And the whole thing is continuous, then our grad students can tell you that at some point it has to be zero. And then there is the solution. And there's a way of solving this thing that bypasses the artificial Euler. There is by, I guess it's by Newton, I have no idea. But it's how to say, well, I start with something, and then I get a root. I think it's even people can parallelize the code, whatever it means, right? I don't know what it means, but yes.
Yeah, I think it was the first time that they proved the existence of harmonic extension
Oh,
by Schwartz.
I see.
Example, suppose you have a union of a square and a circle.
Okay,
It's a very complex geometry. At that time, the people knew how to solve
okay,
circle with representation of the Poisson, the other one
Okay.
FFT. So how to do the union? So they started doing this alternating. So first you solve this, take the trace, solve
I
this,
see.
take the trace.
I
So
see.
Perron is more or less the same idea. So,
Whoa,
so basically now you have to see how to solve a nice domain, maybe a circle or a square locally,
I see.
and then you keep iterating.
Now, this is interesting.
I don't know. Exactly.
This is interesting. This is interesting. I mean, if someone,
75, something like this.
if some of the students want to go to Coimbra, try to help with that. I mean, we have some scholarships. I mean,
For this convergence, you need uniqueness, right?
for
This Bolzano argument. You need uniqueness of argument, right?
yes, yes, but at the level of the method, we have uniqueness. We don't have uniqueness for the limiting PDE.
Oh, so it converts to one solution.
To one solution and gives you somehow a selection criteria, right? That says, well, one interesting thing is to say, well, this consistency gives me an age, right? What if this age is an age Laplace? You see? If it's an age Laplace, is it true that such a solution is better than others, right? So this would be questions to ask. I don't know the answer, but they are cute. Yeah. Yes.
So, thank you very much for this beautiful talk. I have a question related with Carlos' comment, which is, at the end of the story, what you're doing, it's trying to get a function divided by parts and
Yeah.
try to glue it out
Yeah.
an degenerate region
Yeah.
of the domain.
Yeah.
Can you say something about this region? Because the only thing...
Of course not. Of course not.
No,
Of course not.
At numerics level, I say.
Probably. At the numerical level, you can say anything about the solutions, right? You can prove, you just solve the problem and you find the free boundary explicitly. In this example, for instance.
More than the free boundary, what I'm asking is, there is any chance that your method is going to say, okay, your solution is going to decay at some rate, some modulus of continuity?
I don't know.
No.
I don't know.
There is the theoretical over here, which C11 is
Yes.
the best way
Yeah.
to pass, and you know nothing else.
Yeah.
And the second one is maybe dumb question. It's related with your last slide. When you say trigonometrics is when you take your...
The exact solution is a sine times a sine. It's just sine of pi x, sine of pi y. I'm on the plane, so my u of xy is sine of x times sine of y.
Okay.
Yeah.
Okay.
More questions?
Have you tried something non-regular, really non-regular?
We tried.
And it didn't work.
An exact solution, right? An exact solution. And if we go below C1 alpha, it doesn't work. Yeah. But we have a regularity result that is C1 alpha, right? So if you go in C1 alpha, then probably you don't have that guy. Right?
Under C1 alpha, you don't have solution. Because you need to be viscous, so continuous. So if you take a little bit...
I guess so. I guess so.
So thinking in something irregular, it's maybe...
One thing that we want to do is to impose a free boundary condition along the free boundary. Something like the normal derivative in one side plus the other is, let's say, 1, right? I have no clue whatsoever on how to do it numerically.
And also, in your first and in the one-dimensional case, what was your age? Because you said that epsilon was 10 to the minus 4, right?
Yeah, age was, I don't remember, but it's something that is related to epsilon. I think it's should be something like epsilon square or something like this. Has to be such that the age has to be smaller than epsilon, right? Because then you might have, or you must have different points in the regime and you must capture, right? So yeah.
Okay, but then you said that you got a convergence order -4 if your h was 10 -8, something was wrong with the rate of convergence.
No, but I don't know the rate of convergence.
But you said that the convergence was 10 to the minus whatever.
Yeah.
Which is not consistent with the age that you're using, I guess.
I don't know the age I'm using. I have to go to the paper, but yeah. Yeah.
That's fine.
Thank you. Thank you, guys. Yes.
We'll reconvene tomorrow.